Hello, everybody, and welcome to this presentation on algorithms. We'll be focusing on years 3 and 4, and also years 5 and 6. This is the third session, Algorithms Part 1. You may notice that there is some earlier sessions in the series. Please feel free to have a look at those sessions in your own time. Just having a look at the schedule for this webinar. There'll be a few introductions from myself and Nathan. Then we'll do a session overview. We'll look at algorithms in daily life, what's new in the Australian curriculum, version 9, and some activities to explore the concepts. So my name's Chad Ivich. I'm an educator at Grok Academy. I spent 5.5 years, really enjoyed the 5.5 years actually, as a digital technology specialist in both primary school and high school. And Nathan?
My name's Nathan Allison. I'm a lead educator at Grok. I have about 11 years of teaching digital technologies in secondary years. And most recently, I was professional learning coordinator at DLTV, Digital Learning and Teaching Victoria, which is the subject association for Digitech in Victoria.
All right, so today we'd really like to introduce you to the concept of algorithms, highlight the differences in the Australian curriculum between version 8.4 and version 9. We want to present some engaging, ready-to-go activities, hopefully to save you time and to engage your students, and introduce some valid options for assessment. Okay, so when we're introducing a concept to students, it's always nice to start off with the definition. This one's straight from the glossary, the Australian curriculum. So an algorithm is a precise description of steps and decisions needed to solve a problem. Algorithms often involve iterative, repetitive processes and can be represented, for example, as flowcharts and pseudocode. So on the left, we can see it looks like a recipe book, and there is a precise description of the steps that you need to follow down in the method. So add flour, gradually mix in the milk, and add eggs and continue mixing. And we know the amounts because we can see up in the ingredients. Another way to represent this algorithm is with a flowchart. So you start at the top and you work your way down to the bottom. So working through this one, you start, add a cup of flour, ask the question, is there less than 250 mils of milk? If it is yes, add milk, go back, loop back up to mix, ask the same question, we've got milk already, so we move on to no. There are 2 eggs in the bowl, not yet, so we add the eggs, we mix, and we go through the whole process again, and then we finish. That's a nice way to represent an algorithm visually. Another way is with pseudocode. So English language statements that clearly describe the steps of an algorithm. And they can be, hopefully you can implement the pseudocode into actual code in a programming language as well. Why focus on algorithms? They're in our daily life. So for you teachers out there, just wanted you to cast your mind over the last 24 hours. And I just want to ask, how many activities did you do that relied on an algorithm? Just give you a moment to think about that.
So you might want to pause the video here and have a think about, when have you done things that followed a sequence of steps? Maybe some of those steps were repeated depending on the circumstances, or maybe you had to make decisions as part of that sequence. But you probably, when you think about it, you've probably done a lot of things just today that were actually following algorithms.
Yeah, so you might have been using the smartboard in the classroom, or when you went home, you've used social media. Perhaps you went out and you're swing dancing and you're following the steps accurately so you weren't stepping on your partner's feet. Or you might be considering buying a new car and you're thinking, Is this the best deal? Is this the best time to buy, or should I save up some more money and buy the car later on?
Now, what about your students? There's probably a lot of activities you can think that they also do that rely on an algorithm. And next time you're talking to your students and introducing this concept, you could ask them, what sort of things have you done that require a series of steps? Maybe it's having their breakfast in the morning or getting their breakfast organized. Maybe it's catching public transport. Maybe it's something they have to do to get ready to get their laptops going for school. Packing their bag, a sequence of things to put in their bag. There's all sorts of things that we're following a set of steps, and there are different inputs that will vary the way we finish those algorithms.
Actually, algorithms are my favorite concept in the Digital Technologies Australian curriculum, and I love them so much because it challenges you to think in new ways. It's one thing to come up with a solution to a problem, but to frame it in a way that your solution can be processed by a computer requires an algorithm, and that requires you to learn to think in new ways, and what steps will be involved, what decisions need to be made, and what parts of the process need to be repeated or looped over. So moving on, Nathan.
So in the Australian curriculum, designing algorithms is part of a much larger process for creating digital solutions. And when we're looking at a problem or an opportunity that we're trying to address with some kind of digital solution, we have to first define that problem. And then designing the algorithms and perhaps the user interface as well is a sort of a second step in that process. Implementation is when we actually turn that algorithm into code that can be run on a digital device or on a computer. We'll be discussing implementation in the next session. And then a further step in that process is evaluating the solution. If you're planning to teach algorithm, this is a standard slide that we have in all the presentations in this series. Just a reminder that the content descriptions in the curriculum, they're the explicit statements about what needs to be taught. But when you want to assess students and ask how will I know they've learned it, then you refer to the achievement standard for the subject for digital technologies. And when we look at algorithms across the year levels, we can see that this particular concept of algorithms and designing algorithms builds up all the way from years 1 and 2, all the way up to 9 and 10. So you can see where we've highlighted where years 3 and 4 and where years 5 and 6 fit in that sequence. You could almost say this sequence is a bit of an algorithm, you're kind of following through. But at years 1 and 2, you've got being able to follow and describe algorithms involving a sequence of steps. At years 3 and 4, you can see some of the terms get a little bit more complex. At year 5 and 6, we move to being able to design our own algorithms. And then in 7 and 8 and 9 and 10, again, the terminology and the requirements get a little bit more complex. And you may want to visit the 7 to 10 algorithms video to see what's done in those years. What's new in version 9 of digital technologies? When it comes to algorithms, there isn't a lot changed from version 8.4 to version 9. There's a bit of tightening up of the language, but one of the big things that's happened is that the content description we used to see for algorithms has been split up. So it used to be quite a dense one, and now it's been split. So if we have a look at what's actually happened there, you can see the version 8.4 on the left there. Used to have defining, describing, whereas now defining is its own content description there on the right, and follow and describe becomes a separate content description because it's more about generating and designing. And then there's a third content description there that's usually more to do with the design of user interfaces. So the one that's relevant to algorithms basically for today is the one that we've just highlighted there, ACT 9T DI4PO2. Okay. couple of definitions. You may have seen a few of these terms in the content descriptors so far, and if you're new to it, it looks like a whole lot of jargon, a lot of words being introduced. We're going to introduce a couple of those now. One of those is branching. And when you see the term branching, what's really happening there is a decision is being made. In the context of a flowchart, that's where you get that diamond and you break off into multiple outcomes from that decision. So, for example, I'm making a sandwich, or I'm making a number of sandwiches. If I have jam, I spread jam on bread. Otherwise, I spread Vegemite on the bread. So I've had to make a decision based on what's available to me in my pantry. That's the decision I've made in that particular case. So we've branched off into two possibilities, and then we might come back together again to stack the sandwiches up or something. Iteration is another sort of jargon term for basically a loop. It's where we repeat a certain set of steps or instructions in our program. So my loop could be, while there is less than 6 sandwiches, repeat the steps again. In other words, go back, make the next sandwich. Is there still less than 6? Go back again. And I keep going until I know I've got 6 sandwiches, and that means I've done making the sandwiches. If this seems very pedantic and very robot-like, it really should, because that's what happens with designing algorithms. We're designing things so that a computer can carry them out. And that's why it often seems a bit pedantic, because we're actually designing something that's so clear that a computer won't get it wrong. So when we look at the achievement standard for years 3 and 4, we can see that it's highlighted there, the section that's relevant. Students follow and describe simple algorithms involving those two things: branching, making decisions, and iteration, repeating steps. And Chad's going to introduce an activity that can be used for just addressing this particular part of the achievement standard at years 3 to 4.
Thanks, Nathan. Yeah, there's an activity called Lego Algorithmics. I have run this in the classroom a few times, and I know that kids love it. It's a great activity for getting them to follow along and describe algorithms. It's great for grade 3 and 4. You could also use this for grade 5 and 6 with more complex Lego kits and instructions. So what happens is they build some Lego in pairs together, but there's a catch. It's a bit trickier than usual. So the builder can't see the instructions. The builder's the only one that can touch the Lego bricks, and the instructor can only use words. They're not allowed to point at the pieces. Second time round, they swap roles. So the builder and the instructor will swap roles. And so by doing this, students will hopefully link instructions to the concept of the concept algorithm, and they'll also get better at clear instructions and clear communication skills.
It's one of the cool things about this. I've supervised groups of teachers doing this activity, not so much students, but one of the cool things that happens is that you see people coming up with their own language for talking about pieces. It'll be like, oh, that's the yellow slidey piece, or, you know, that's the 2x4 flat piece, or whatever it is. They have to come up with their own specific language for referring to each of the parts.
Yeah, I like it, Nathan. Thank you. Yeah, we went through that challenge ourselves describing the orange grill bit, didn't we?
Yeah.
Okay, so running this activity, first of all, you can find it on our website. You can see the link on the left there. What you need to do, though, before students start building is just like a 1-minute strategy discussion time before they touch the Lego bricks. And it's actually a race as well. So if a team finishes, a pair finish before others, just allow the others to finish off. So this is what Nathan was referring to before. So and what the students will see as well. So what sort of language would you use to describe to your partner, your builder, so they knew which pieces to pick up and where they knew where to put them? It's your role as a teacher to check if the builders followed the instructions precisely. So a student has come up with the plan on the right. I'll just give you a moment to see if you can spot any differences between the final instruction number 8, and the final build. Just give you a moment to have a look. Where the builder's gone wrong is they've placed the orange piece. You can see it's too far back from the propeller. It just needed to be more forward. There's actually two orange pieces. So if we go back in the instruction book, go back to instruction number 3. Oh, go forward. Yeah, so if we go back to the instruction book, you can see the builder has not lined up the 2x2 grey block with the orange grills. Or you could say the orange grills are placed too far forward. Once you've the students have gone through the activity once, it's great to have a class discussion. Some really useful questions are, who found that easy or difficult and why? And it'd be really nice to ask students the words they use to identify the pieces. Hopefully you're listening and you start to hear students using, particularly towards the end of the activity, really specific language like the 2x6 yellow Lego piece. Yeah, so on the lookout for really specific language to make it easier for the builder. And then so you run the activity again, you swap roles. This time there's no opportunity to discuss strategy. So run the activity twice, and then at the end of the second time, you have a second class discussion, and you ask students, what they did differently second time and how they applied what they learned from the first time. And what I noticed running the activity in the classroom, the second time round, the build happened a lot quicker. Students were using much more precise language, and it just seemed to happen a lot quicker and a lot easier, and yeah, just more efficient. And providing really clear instructions is such an important skill, especially as students move through the curriculum into grade 5, 6, and grade 7 and 8. Computers are incredibly fast and accurate, but they are dumb. They need very, very, very detailed instructions before they're able to solve problems. And yeah, before students are using text-based languages like Python and JavaScript, and yeah, they want to get good at providing really clear instructions, because a missing colon or parentheses in those languages means the program doesn't run. Also like the activity because it's visual, it's tangible, and it's verbal. So students, the instructor can see when the build's starting to go wrong. Students love learning by tactile learning, and they're working on their verbal communication skills. This activity also links to what we're going to be doing next week when we're looking at implementing an algorithm and a program. We're working with specific language to build up the program so that the computer knows what to do. If you were planning on running this activity, we would recommend using Lego packs of about 50 pieces with simple Lego instructions like the green book you can see on the right. If you don't need to race out and buy new kits, you might have some already, and you can just click on the Lego link there to find the instructions for the specific kit that you may have at school already. We found this talking assessment, we found this self-assessment idea on the Digital Technologies Hub. So students consider the algorithm designed to instruct their partner and the one they followed, and they write down 3 things they learn about providing step-by-step instructions. How could they make the instructions clearer? And some suggestions might be shorter instructions or really specific language, as we said before, like the 2x6 yellow Lego, 2x6 yellow Lego piece to distinguish it from the other two yellow pieces. And just looking at the verbs in the achievement standard on the right, the builder is following the instructions, and the instructor is describing the algorithm with the words they're using to describe the Lego pieces. The instructor is also going through an iterative process. So they're checking at each instruction, let's say it's instruction 4, that's been done correctly by the builder. If not, they need to make a decision and to somehow stop the builder and get them to place the piece in the correct spot before they move on to the next instruction.
We're going to take now a bit of a look at years 5 and 6. And once again, look at the differences between version 8.4 and version 9 of the Australian curriculum. In this case, it's a little different to what happened in years 3 and 4. So we still have this splitting happening. But what's happened this time is that the design of the algorithms and then implementation have kind of been split up a little bit. So you can see that the original version 8.4 content description on the left is a lot more in it than the one on the right, which is just saying design algorithms involving multiple alternatives, which is branching, and iteration. So a lot of the other terminology and content has been moved into a different content descriptor about implementation. Also, the one below there, once again, looks at designs. It's still part of that generating and designing, but the one at the top right really is the one that's relevant to algorithms there. So if we look at the achievement standard for years 5 and 6, the highlighted part again, students design algorithms involving complex branching and iteration. So what's changed from 3 to 4? Well, we're now designing algorithms, not just following and describing them. In other words, the students are having to come up with steps to make something happen. And we use the term complex here. So branching is no longer just one decision, but perhaps nested series of decisions that have to be made for the right outcome. I think Chad's going to introduce to us another activity.
Yeah, this activity looks fantastic, and it does have the opportunity for students to do complex branching and for them to design their own algorithm. So it's an offline, unplugged board game with the aim of going from the start and finishing at the finishing star. The students move their way over, I guess, smaller if mountains. There's a series of those as they go up the bigger if mountain, and to go through the process of rolling a die, seeing what number they get, and making their way through the flowchart to know what to do next, whether they're passing the small if mountain or they're staying where they are waiting for their next turn. The flowcharts actually are mimicking the decision-making process of computers. So we'll just go to the next slide, and we'll just before we go off to the Grok website, there's the things that you need on the left. I have printed out the PDF for the board game there, and I have the mountain in the E mountain on the E squares on the board. I haven't put mountain A, B, C, D, and F on there just because I wanted you to see the whole board, what it looked like. But that's what it'd do when you cut out the templates, and you'd have your 6 mountains on there. We'll just go off to the website now and have a look at the activity. And we'll just go down to so we can have a bird's eye view of the whole board. Yep. Excellent, thanks. Yeah, so yeah, as we were saying before, you're making your way up from the start all the way up to the finish, and you're having to climb all these small if mountains along the way. If we go down to a little bit further, Nathan, to A, the flowchart A, if we can zoom in a little bit. So this is what you cut out and you stick on the board. And we'll go through the process of going through the A mountain flowchart. So if you were to roll a 3, you could ask, the question is, did you roll less than 4? The answer is yes, so you may pass. In that case, you pass. If you were to roll a 6, did you roll less than 4? The answer would be no, so you just have to wait for the next turn. The flowcharts do get more complicated as you go from A all the way up through to F. If we could just have a look at C. I'll go back, yep, C, yep. So if you were to roll a 5, for example, we can say, does the roll equal to 2? No. Does the roll equal to 4? No. Does the roll equal to 6? No. So we have to wait for our next turn to do the roll. Let's say we rolled a 4. It was our turn again. We rolled a 4. Does it equal to 2? No. Does roll equal to 4? In this case, it's yes. So we can pass mountain C. So making our way up the mountain. If you were interested in introducing variables to students, probably in grade 6, the F mount's a little bit more complicated. So whatever you roll, if I was to roll 3, X becomes a 3. If I was to roll another 3, Y becomes another 3. So if we use that example, is X plus Y more than 10? No, because it's 6. So is X plus Y less than 3? No, because we rolled 6. Are X and Y equal? The answer is no. So we roll again next turn. If I was to do it again and roll a 6, X would become a 6, and roll again 5. Y would be the 5. So that's 11. Is X and Y more than 10? Yes, and then I could pass. Something else I wanted to show you is these same flowcharts are available in Python syntax, and it's the exact same logic. So if we have a quick look at mountain F again. There we go. Yep. So it's the same logic. It's just the flowchart is rather than using the symbols, it's written out in the Python syntax there.
So this might be if you were extending students, or you could use it in 7-8. But if you were extending students in 5-6, you really wanted to get onto some general purpose programming like Python.
Excellent. Yep. So we'll go back to the next slide. Oh, cool. Yeah. So I haven't actually run this activity in the classroom. So I reached out to another Grok educator, Bianca, another fellow Grokker, for her experience of running this activity in the classroom. She said students really enjoyed playing the game. And after they had a few turns with the game, they were confident enough to create their own algorithms. And as we saw before, this activity is great for extending students who want to transition from visual programming to text-based type programming, like we saw with the Python example just before. Okay, so regarding assessment, we're trying to encourage in grade 5 and 6, we're trying to encourage students to create their own algorithms. So the rolling of the dice may or may not be the deciding factor. So they could come up with a different, like a little mini game, if you like rock, paper, scissors. Or they might have, if they're in, you can see the one on the right, are you in first place? And then the number on the dice is the deciding factor, what happens next. I just wanted to point out the one on the flowchart on the right has complex branching. So there's a decision, are you in first place, is flowing on to either did you roll a 6, or if the answer was no, did you roll less than 4? So that's something that's expected at the grade 5-6 level. Something you could do if you're asking students to design their own algorithms is a little template like this, and then they could decide on the mini game that they want to put in there. and then decision, and then possibly the next one that they design could have the complex branching as well. If students were, or what you'd be looking for in the students' work, in the algorithms that they design, are that they can consciously make the flowcharts harder to, or the last two flowcharts a bit harder, like E and F, so they know the logic. So for example, it's much harder to roll a 6 than it is to just roll a number above 3. So you just want to check that they understood how to make the flowcharts a bit harder to pass towards the end of the game. Oh, sorry. Yeah, just go. And something else that you're just checking for in students' work is that they do have those complex branching, so a decision flowing into another. Something else you could do to check for their understanding is to translate their flowchart that they design into a procedural text that is has the steps in there and action verbs like roll and make a decision and move the token and so forth. We haven't really, if we look at the achievement standard, iteration is part of that as well. So we've been looking at how students can design algorithms involving complex branching. Part of the game has a loop that you can get stuck in, and you need to roll a 4 or more to exit the loop. So if you, in students' work, you might want to check that they haven't got themselves or another player in an infinite loop by maybe, you know, that they had the question was, did you roll a 7? So if they that's not really possible because there's only 1 6 on the dice, but you'd want to check the student's understanding if they said 7, because it'd be, yeah, the player would be stuck in the infinite loop.
The next activity, this is probably more of a class activity that we're looking at for the years 5 and 6. And I'm going to start, this is a number guessing game, so I'm going to use Chad as the guesser here. So Chad, I'm thinking of a number between 1 and 100. Have a guess and I'll tell you if it's lower or higher or correct.
Okay, cool. I'm going to go with 52.
Higher.
70.
Higher.
Okay. 87.
Lower.
I'll go with 80.
Higher.
Oh, getting there.
Getting close.
Yeah. I'll go with 85.
Lower.
Oh, 83.
Correct. All right. So, so that's an example of a number guessing game. As Chad and I were playing that, and obviously you can play this with your students, but as Chad and I were playing that, you might have been thinking about what was going through Chad's head as he was trying to keep track of the number that what the next guess should be. And this begins, I guess, as a class discussion, but we're basically considering what would happen if the computer, you're playing the game, but you as the human, you're the one who knows the number, and the computer is the one that has to try and guess it. So you're saying to the computer, I've got a number between 1 and 100. The computer doesn't know what the number is, but it's going to try to guess it. All it can do is respond when you say higher or lower or correct. So you might ask these questions in the class discussion. What does the computer need to tell the player to do as part of this guessing game? So it might tell the player, think of a number. It might tell the player, is it this? And, you know, what does it need to ask the player for? What information does the player need to give to the computer so it can make its next guess? And then what should be its strategy for guessing? You might Chad had a bit of a strategy going there if you have a think about what he was doing as he was guessing. And your students would also come up with strategies to find the guesses quickly. So what should be the strategy, the ideal strategy for a computer if it's going to try and guess this? And in order to make that strategy work, what things would the computer need to remember? What was Chad having to remember when he was trying to guess that number? If you want, you can pause the video here and have a think about it yourself. One of the interesting things we discovered when we were looking at the Climb Up If Mountain lesson is that in the very same PDF document, there's an activity that's all about finding this strategy. So on the Grok website, that link takes you to the same document, and it's the very next one in the document, and it does have a strategy there for a number guessing game. So I'm now going to go on and actually write the steps for the game, because this is where we ultimately want to get to with the students. So the first thing that needs to happen is the computer is going to tell the player to think of a secret number between 1 and 100. So the computer is going to go, you think of a number, don't tell me what it is. Now, the next thing that's going to happen is the computer has to remember a lower boundary. And this is a variable. This is something the computer is going to have to keep remembering. It's also going to have to remember an upper boundary. So this is an upper limit to what the number could be. So both of these are things the computer needs to keep track of. And then this is kind of the key part of the algorithm here. The computer makes its guess. It will always be halfway between the lower and upper. So the ideal first guess between 1 and 100 would be 50 or maybe 51. That would be right in the middle. Then the computer is going to ask the player if it is correct, too high or too low. And there's 3 possible outcomes here. So this is complex branching. We've got 3 possible outcomes. The player could say, you got it right. That was a lucky first guess. The game is over. Or the player could say, that's too low. Now, what does it mean if the player says that's too low? So initially, Chad said 52, and I said too low. So what did Chad guess next? I think he guessed something like 70, 76 or something like that.
Yeah, I think I went up to 80.
Or 80. So what Chad did was he adjusted. He knew now that he wasn't going to be below 52, right? So he adjusted his lower boundary so that now he was looking somewhere between 52 and 100. And so we changed the lower boundary and we go back to step 4. We make another guess. But now we're going halfway between the new lower boundary, 52, and the upper boundary is still 100. And we're looking at halfway between those two. Now, if the player has said too high, instead of changing the lower boundary, we change the upper boundary and go back to 4. And eventually, by this kind of process, we will get to the correct answer, as long as we're using whole numbers. Now, bit of terminology here. In computing terms, this is actually called a binary search. We're always looking halfway between the available numbers to get to the number we want. So that's quite a nicely placed algorithm to be challenging for years 5, 6. It does involve iteration, it involves a loop, but it also involves a bit of complex branching. If we think about how we would design this, I've just kind of scattered the pieces of the flowchart all over the place there. If we wanted to put them into a nice order, you could make it an activity to get the students to put these pieces into the right order. But basically, this is the right order here. Just basically the same thing as what we had in our description on the previous slide, but now it's in the form of a visual flowchart. Think of the number, set the lower and upper bounds, make our guess. Is it correct? And then depending on what they say, we change one of those boundaries and we try again until we get it right. All right. So that's a sort of an activity. We're going to return to this activity in the next session when we do implementation. We're going to have a look at how this activity could also be implemented as a program in one of those visual programming languages. The only other example I've got, and this is, since the last one was kind of numeracy related to maths, this one is more related to English or literacy, and it's a choose your own adventure story. If you've never played around with PowerPoint, this is really cool, and the same thing works with Google Slides. You can create links to take you to slides. So if I was to click on one of these links, it will take me to a particular side. So you're standing at a fork in the road, go left or go right. I'm going to go left. Actually, I'll go right. And it takes me to a dark cave. It's really very easy to set up these links in PowerPoint. There's lots of lessons to show you how to do it. And lots of links out there is one of the basic functions of PowerPoint. So you can certainly find out how to do it. But using this, you can basically have your students put together a choose your own adventure story. One of the things I used to do I actually did this with year 7, 8 students when I was teaching, but you could certainly do it with 5, 6s, is you can give them, this was an A3 planning sheet that just has the slides numbered on it. And the students would write inside what was going to happen on that slide in the story. And they had to draw arrows between the slides to indicate where they were going to go in the story. I've arranged them in a circle because it just makes it easier to draw arrows from slide to slide. But yeah, some links to content descriptions in the English curriculum to do with creative writing. And yeah, this is a really interesting way of doing sort of a precursor to writing for video games as well. So it's a really interesting kind of look at how fiction can be different when there's interactivity involved. If you're ready to move on from just using PowerPoint, there are also dedicated free tools. So one of the most popular ones out there is a tool called Twine, and there's a link there to Twine there. It does allow you to do highly sophisticated branching stories. And of course, we are doing branching here. That's the whole point. And loops are possible by going back to the same place, but a large part of interactive fiction is just the branching aspect, making a decision about where to go and what to do next. Just be aware that websites like Twine are not made specifically for kids. So some of the fiction on there that other people have made was probably not going to be at all suitable for kids, and that's worth noting. Yeah, but it's certainly a tool that can be used. That was the end of our examples. So yeah, Chad, did you want to take this one?
Yeah, as teachers, it's good to be aware of misconceptions that students might have coming into your digital technologies class that's focused on algorithms. One of them might be algorithms are characteristically complicated. We've seen a few today in our activities that aren't complicated. Another one is algorithms are understood by few who have secret knowledge. Yeah, there's opportunity. We can start off with simple algorithms, like with our students, and just follow algorithms and eventually modify and then design and just build your way up to the more complicated algorithms. Algorithms are mysterious. I think today's webinar is debunk that one, but so the truth is we use algorithms every day. It's unlikely you'd put on your shoe before you put on your sock. Some order matters, particularly in that situation. So there's an example of a really simple one that we do every day. Is we wet the toothbrush, apply toothpaste, put your brush in your mouth, brush your teeth, and rinse. And so Nathan's just going to talk about misconceptions for teachers.
Yeah, so particularly this is an interesting kind of controversy sometimes among maths teachers about what algorithms really mean in terms of what they teach students. When it comes to learning about algorithms, what we're doing in the digital technologies curriculum is much more about helping students to create their own algorithms. It's not just about sort of rote learning and following steps. It's also about actually teaching students to do what we call algorithmic thinking or computational thinking, where they're expressing something that needs to be done in a way that a computer can carry it out. It's an important skill that we're doing in digital technologies. So it is a lot more than just a superficial understanding of things, but it's about solving a problem in a particular way. And in this case, that way is to turn the solution or turn the problem into an algorithm that can be solved. We've linked a few resources at the end of this slide, and these three, I'd like to just point out the first one especially. It's great. It's an unplugged activity where you work with a barcode and you understand why barcodes have a certain series of numbers, and they always have a particular number at the end that connects with the numbers before it, so that you know if you've got a bad reading. And it's a maths type of thing where you work with the numbers in different ways, add them up and times them and stuff, so that you can check that that last number is always correct. And it's a great activity, and you can also implement it. But another couple of resources there. There's an algorithms whole topic on the Digital Technologies Hub. You can follow that link to get to that, with lots of lesson ideas for doing a bit of algorithms. And then there's also the Beveris challenges hosted by CSIRO in Australia. These are not in any particular coding language. They're actually general algorithm problems, and a great way of getting students into some algorithmic thinking. There's ones that are done sort of as a competition or as a sort of challenge each year, but there's also ones that are available every year from the past years. So it's really worth checking that out as well, maybe even as kind of a learning hook or a kickstart at the start of a lesson.
Okay, so just looking forward next week, we're going to look at algorithms part 2, which is implementation. So translating the algorithm into a visual program that can be executed by a computer. And the 5th one is privacy and security. The 6th one is data collection and analysis, secondary, and digital literacy for primary. And the last one is designing and assessing digital technologies projects. Just wanted to let you know that for Australian schools, all the courses, resources and content are now free. A partnership was struck between WiseTech Global and Grok Academy last year in October. And we encourage you to take advantage of those free resources, and look forward to
Grok. Grok's mission is to educate all learners. And this is kind of our mission statement, to educate all learners in transformative computing skills, knowledge, and dispositions. So this partnership with WiseTech does remove that financial barrier to schools in using the Grok resources in Australia, as well as allowing us to expand our team. This last slide has our contact information. And please get in touch with us if you have any questions about these sessions. And we'll see you next time.